So in this video we'll explore the iodine clock reaction, which is an equilibrium reaction that suddenly turns a clear solution black. I will then proceed on with explaining some basic reaction kinetics, but I will also explain the formation of the famous starch polyiodide complex, which is responsible for the color change. For safety purpose, I've listed all H and P's of all chemicals involved. As soon though as you got the diluted solutions, there's really no danger and the solutions are pretty safe to handle. Also worth mentioning is that the reacted mixture can be safely poured down the drain. So in terms of chemicals, there are three basic solutions that we have to make. These solutions are then mixed and a color change occurs. Also worth mentioning is that the starch solution has to be boiled or you won't really get the starch into solution. You also have to filter the solution again because starch is really not that soluble in water. To begin with, I've tested the effect of the starch solution on the color change. I've therefore set up two test tubes and added equal amounts of solution A and B, but different amounts of solution C. To the one on the left I've added 0.5 moles of solution C, and on the right I've added 1 milliliter. As you can see, the one on the right had a much more decent color change, so I stuck with 1 milliliter for the whole experiment. So nextly I wanted to demonstrate the effect of the different ratios of solution A and solution B. So in this shot you can see the different ratios, but also the time needed for the color change to occur. As you can see, with a higher concentration of solution A, we get a much quicker color change. So I've also tested the effect of the temperature through the reaction kinetics. I quickly set up some test tubes, this time with the same amounts of solution A and B, and heated some of them. As you can see, higher temperatures are resulting in a quicker change. Also interesting is that the one on the right with the temperature of around 80 C has no real color change, and why I will explain right now. So, as we mix the three solutions, we have the following reactions going on. Firstly, the iodide ion is reduced by the hydrogen sulfide ion to produce iodide ions. This reaction is pretty slow though, and therefore only a small amount of iodide ions at the time is released. The iodide ion is then oxidized by the remaining iodate to iodine. This reaction is quite fast, but even faster is the competing reaction where iodine is reduced by the hydrogen sulfide ion. Because of that, iodine can't really complex with the starch until all of the reducing agent is used up. When we finally reach the point where all of the reducing agent is used up, iodine by itself can react with another iodine ion to produce polyiodide ions. As you can see, there are technically infinite molecules of polyiodide ions, so I9- is also possible, and it's not only stopping at I7-. So on the left you can see amylose, one of the major components of starch, and it's made of by repeating glucose units. These long chains are bonded in a tetrahedron angle, so it forms these helix structures. The polyiodide ion can now embed into this helix structure and can form a so-called charge transfer complex. This complex is held together by the difference of electron density. The electrons in this iodine complex are delocalized, and therefore it reflects this really nice looking blue wavelength. Generally, you can say that the formation of this complex is exothermic, meaning the reverse reaction is endothermic. That means that the complex is broken at elevated temperatures. This explains why we've only seen the iodine-like color, but no starch complex at a temperature of 80 C.